All right, in this video we are going to expand on what we can do with thermochemistry by learning about calorimetry. And just like when we are in lab, we can't measure moles directly. We've been talking about these units of energy, kilojoules, and there's just not a kilojoule measuring device. So talking about enthalpy in some ways just doesn't seem real because we can't measure it. Well, calorimetry gives us a way of measuring enthalpy changes in an indirect way. And then you get to learn a cool new word. So just like, imagine if you use calorimetry and stoichiometry in your daily speech, how smart you'll sound. Okay? So what calorimetry is just they're experiments that are designed to determine how much enthalpy change of reactions they have. If you look at the word calorimetry and think of like calories, which we talk about quite often in terms of food, so calorimetry gives us a way of measuring calories by measuring temperature changes in reactions. So the important formula for calorimetry is Q equals MC delta T. So this delta, you saw it with the enthalpy 2, and I don't know if I didn't make great strides to point out. Delta, so this triangle here, that's the Greek letter delta. And in science, whenever you have delta, it means change of. Okay? So delta T is the change in temperature. So that triangle is not something you put a number in for per se. The delta T is something that needs a number. So a lot of times in the past, people always call this MCAT because the delta looks like an A, and if that's how you want to remember it, fine, but it's not an A. So Q is going to be either the heat coming in which case Q will be positive, or the heat leaving a substance or that's a process, and Q is measured in joules. M is the mass of the substance measured in grams. C is the specific heat of a substance. So this is something new that we haven't talked about, specific heat. And it's measured in joules per gram degrees Celsius. So if we look at, for example, water in units not of joules per gram degrees Celsius, but in units of calories, water has a specific heat of 1 calorie per gram per degree Celsius, because that's actually how a calorie, a little c calorie is defined, is the amount of energy it takes to raise the temperature of water by 1 degree Celsius, of 1 gram of water, 1 degree Celsius. If you want to look at a big C calorie, that's actually the amount of energy it takes to change 1 kilogram of water 1 degree Celsius, because it's 1,000 times bigger. In units of joules per gram degrees Celsius, water has a specific heat, and this will probably come up later, of 4.184 joules per gram degrees Celsius. This is a really important number because we do experiments with water all the time, and on worksheets and things, I am not going to give you this number over and over and over again. Every time water shows up in the problem, you're expected to know the specific heat of water is 4.184 joules per gram degrees Celsius. Okay? Then delta T, temperature change, again measured in degrees Celsius. Technically, you really should measure temperatures in Kelvin, but since we're looking at differences in temperatures, doesn't matter. And then delta T is defined as the final temperature minus the initial temperature. Actually, always a delta anything is always the final of that. Subtract the initial of that. Okay, so again, I've already talked about specific heat a little bit. I already gave you that. So here it is in a couple different places. When we look at, so that Q equals MC delta T, that looks at how much heat must be coming or going from a substance when it's being heated up. When we have a process, so like a chemical reaction, and I'm breaking and making bonds, so there's not a thing that's absorbing and releasing the heat, it's being released or taken in by those changes in bonds and stored in the bonds or being released from bonds. The formula we use for Q is a little bit different. And Q is either equal to the moles times delta H or the mass times delta H, just depending on which units you want delta H in or which units you found delta H in. So oftentimes for chemical reactions, when you look them up in books, a lot of times they're given as in per mole. But things like, for whatever reason, when I look up what the enthalpy changes for melting ice or creating steam from water. A lot of times those are on a per gram basis. And so it would just depend on what you have. But we know how to go from mass to moles really easily anyway, so it's not like that's a big deal. The other thing that's important with calorimetry is the first law of thermodynamics, which states that we cannot create energy, we can't destroy energy. Any heat that leaves one place must go somewhere else. And mathematically, that looks like you add up all the heat. So remember, Q is the heat. So basically, I could restate this in words like the heat leaving the water plus the heat entering the cup equals 0. Now this is kind of a weird way of saying this. I think a lot of times most of us would think of it, instead of having it like that where the heat plus heat is equal to 0, we would probably look at it like, want to look at it like this, where the heat leaving one place is equal to the heat entering. And you can do that when you only have two things exchanging heat, but a lot of times we have more than two things exchanging heat. The other problem with doing it this way is that technically the heat leaving the water would have a negative sign, and then when the heat entering the cup would have a positive sign. So basically you'd have a negative number equaling a positive number. And of course you can solve it and put negatives in there to fix that. But for this class, we're going to say they add up to be 0, because one must be positive, the heat leaving the water is going to be negative, and the heat entering the cup would be positive in this situation. Okay? I'm kind of tired of writing in red. Looks really mean. All right, when we're doing calorimetry problems, here's the steps. Figure out what's interacting, figure out if that interacting thing is a substance or a process, put all known quantities in, and solve for the unknown. So you'll have these written down. I don't need to spend time on them. All right, so here's an example problem. We've got water, we put it in a calorimeter. The two come to a temperature of 15 degrees Celsius. Then I take the other water that's at a different temperature and I pour it into water, and they reach a new temperature. Now, if I have one sample of water and it's at 15 degrees Celsius, and I have another sample of water and it's at 45 degrees Celsius, and they're the same amounts of water, you might expect that they would just come to a temperature halfway in between the two. And if it was a perfect world, you would be right. They should come to 30 degrees Celsius. However, the cup, the calorimeter thing that cold water was sitting in, is going to take some of the hot water's heat also. So when I look at what's exchanging heat, I've got cold water exchanging heat, I've got hot water exchanging heat, and I have the calorimeter is exchanging heat. Once I figure out what's exchanging heat, now I write the first law. So, since the cold water is exchanging heat, I write a Q for it. So whatever heat goes into the cold water is being represented by Q of cold water. The hot water is exchanging heat, so it gets a Q. Okay, so whatever heat comes out of the hot water is being represented by this Q. The calorimeter is exchanging heat, so it gets a Q. Whatever energy goes into the calorimeter is represented by that Q. And again, all of these have to add up to 0. Okay? Now, with the proper expression, cold water is a substance. Substances, Q's equal MC delta T. Hot water is a substance. Calorimeter is a substance. Now, we don't care what the mass of the calorimeter is, and it'll always be the same every time we use that calorimeter. So I just lump the mass into one term, and I call it CCal. And so this CCal is really MC of the calorimeter times delta T. And to be technically speaking, this C and this C are called specific heats, and this C is called a heat capacity. Who cares? It's a term, okay? Just know for calorimeters we don't worry about the M. Some people care. but you don't care. Now we put in the numbers, okay? What is the mass of the hot water? Well, I read through the problem and it doesn't say grams anywhere, and then I freak out because, oh my gosh, you didn't give me grams. Okay? Thing is though, water has a density of 1 gram per milliliter. And so if I have 25 milliliters of water, I have 25 grams of water, close enough for us. So the mass of the cold water is 25 grams. Specific heat. Doesn't say specific heat anywhere in this problem. Again, I'm never going to give it to you. 4.184 joules per gram degrees Celsius. Temperature change of the water. The water starts at 15 and it ends at 28. That means it went up 13 degrees Celsius. All right, hot water, mass. I don't have much time, so I better go fast. 25 grams, 4.184 joules per gram degrees Celsius for the hot water. Temperature change of the hot water, it went from 45 down to 28. That's a drop of negative 17 degrees Celsius. The calorimeter, I don't know the C-cal. That's the point of this problem. Okay. The delta T of the cold water, since it starts in the calorimeter starts in contact with cold water, is 13 degrees Celsius. Okay. All of this, don't forget to set equal to 0. You do some math, you get the C-cal. Try it out. Come back to me. Tell me how you did. All right. So there's other example problems we can work out. We're not going to have time here to do all these. I just want to focus on this one where I have a reaction. So I have 0.1 moles of HCl is reacted with 0.12 moles of NaOH. The total volume of the solution is 100 milliliters and it starts at 25 degrees Celsius. What will the final temperature be if the delta H of the reaction is negative 56 kilojoules per mole? So first we have to look at what's exchanging heat. Well, the problem mentions HCl. It mentions NaOH solution. Okay? It mentions a reaction. It doesn't mention a calorimeter because we're assuming it's a perfect calorimeter and we don't care. Now, when I react these two things together, when I'm all done, I'm not going to have them anymore. So they can't change temperature because they won't be there. So what they are going to make is a solution of products, and that's all I care about. So when I do this one, I'm going to say it's just the Q of solution is exchanging heat with the reaction. Okay, is what I'm going to look at. The solution is a substance that has a mass, a specific heat, and it changes temperature. The reaction is not a substance, but we're using a certain number of moles, and we're multiplying by delta H. Okay? Now, the mass of it, again, we weren't given the mass of the solution. We were told the total volume of the solution offers 100 milliliters. Now, the solution is not water, but it's mostly water, so this would be 100 grams. Again, the solution is not water, but it's mostly water. So I'm going to put in 4.184 joules per gram degrees Celsius. And I know that this is wrong, and I'm going to get the wrong answer, but it's high school chemistry, and I'm going to get an answer that's close enough for high school chemistry. The final temperature, I don't know the final temperature, so I'm just going to leave that as delta T. And moles, I have to use the moles of the limiting reactant, which is the HCl, because I have the least amount of it, so 0.1. And for delta H, I have to put in negative 56,000 joules per mole, because I need agreement between the units. And then I'll solve that one. So we're definitely probably going to have to work some examples of these in class, but you'll come into class having some background, and we'll see what we can come up with.